Hello, Fusion fans. Today we have a very special interview with Dr. Jaeyoung Park, CEO of EMC2. I think the most interesting work EMC2 is doing right now is their simulations. Dr. Park will be discussing that with us today. The code that they have can simulate 1 billion particles while maintaining the total energy of the system. This could provide a powerful tool for fusion researchers around the world. The first question I have for you is, can you introduce your company and explain your contributions to fusion?
Thank you for inviting me. The formal name is Energy Matter Conversion Corporation. It's actually a for-profit corporation with about 20 shareholders, and it dates back to 1984. It was started by late Dr. Broussard, and with the goal to make practical fusion power based on a concept now known as Polywell. The Polywell concept evolved over the course of the last 30 years. During the time, EMC2 built and operated about 20 fusion devices. So as a result, EMC2 now has a very clear idea about how to make a Polywell fusion reactor. It's a shame that Dr. Broussard is no longer with us, but we made a tremendous progress over the last few years, and I think we're getting closer to the goal of making a net fusion energy generator. I often tell people to read about Polywell fusion from Wikipedia article. We did not actually contribute anything from the company end of it, but it does contain pretty good history. The information there is largely accurate. We're pretty slow in putting out information on the net. I've been really busy, but I'd like to give some update about where we are today.
In 2014, you published a very important paper in Physical Reviews X, and I guess it's worth explaining what you did and what were the major conclusions of that work.
The experimental work described in the PRX paper is a major milestone for us. We've gone through setup experiment from Wiffle Ball 6, Wiffle Ball 7 to the Wiffle Ball 8. While the Wiffle Ball 6 and Wiffle Ball 7 machine produce significant amount of neutron from fusion reaction, if you look at how many fusion events we created, the fusion yields were not very big. So with the strong support from the Navy at the time, we built and operate the WB8. And it was a major upgrade, and the goal is to greatly increase the fusion yield. What we learned was we had trouble, and we will not be able to heat the ions well with high voltage bias on the grid. And that was a big finding. If you cannot heat the ions well, the confinement of the plasma becomes irrelevant in a fusion event toward the goal of the fusion energy. So we went back to the basic drawing board to find a way to heat iron. That's why we started a setup experiment that eventually led the PRX paper. You have to heat the ions to hundreds of millions of degrees. To do that, you can either operate with a high voltage bias on the grid. That is the case for the WB6, 7, and that's what we try in WB8. Or with electron beam injection envisioned by Broussard. And what we learned out of the WB8 is we couldn't really heat the ions well with the bias voltage on the grid. So since it didn't work, we then pursued the electron beam injection as outlined by Broussard. So we inject electron beam in the WB8, and turns out the confinement of the electron beam was poor. And we tried to increase the magnetic field, play with the beam location, and none of them seem to work very well. And it's mainly because the electron beam moves really, really fast. The beam energy we used was a 7 kilovolt beams. The electron beam velocity is already over 1/10 of the speed of light. They bounce around inside the device very, very fast. So at that time, the confinement is poor because after just a few dozen bounces or so, electron beam leak it out of the plasma. If we cannot confine the electron beam, we couldn't really use the electron beam to heat ions. So that's where the Wiffle Ball comes in. The motivation behind the PRX paper was we really need to produce the Wiffle Ball. And once we produce the Wiffle Ball, it should help the confinement of the electron beam. Otherwise, we'll never get a heating that we need to make a fusion. So to do that, we inject a very high power plasma for a very short period of time, so we can inject a lot of plasma, basically pressure inside a magnetic trap. That changed the magnetic field and formed the Wiffle Ball. Once it did form the Wiffle Ball, we were able to confine the electron beam. We couldn't do it before.
Can you describe what the Wiffle Ball is to people who don't know anything about it?
The Wiffle Ball is if you inject a very high pressure plasma into this cusp magnetic field produced by the coil, plasma will modify the magnetic field dramatically. So you now have an equilibrium magnetic field between plasma and magnetic coil magnetic field, very different from what you start with. And it actually literally looks like the ball. If you look at some of the more recent simulation we did, we can actually visualize almost like the ball-like structures inside the device. So in that space, plasma does get contained because they don't really have an easy access to move out of the reactor. So that's what we call Wiffle Ball. And Dr. Prasad has a very interesting cartoon. You start with the device. By injecting plasma, you start expanding the whole system. And one property of that is it'll slowly close down the hole toward a very small size. That looks like the children's wiffle ball they play and learn how to play baseball. Historically, the better known as a high beta cusp equilibrium magnetic field. It's technical kind of word. In a certain magnetic field system, the presence of high pressure plasma will modify the magnetic field that helps to close down the losses, sort of the losses of the magnetic system.
You said you wanted to provide an update on the company. That paper came out in 2014. Can you give us a sense of what's happened since you put out that paper?
With the new understanding about how the wiffle ball works and what it can do for the Polywell, we spent probably about a year or so to look at all the reactor configuration. Because eventually, at the end of the day, we want to produce the fusion energy. So we went to the material study, we went to the breeding system, we went to the power generator design and power plant design, and we find out that, well, if the wiffle ball works as we hope, this will be a really great fusion reactor. The electricity costs will be comparable or cheaper than natural gas. So that was the first part of the exercise we did. We did that exercise probably about a decade back at EMC2. So we wanted to redo those data to know exactly where we stand. You just have to make sure that you're on the correct path toward making a practical fusion power. So we spent about a year, and some of that information that we share, but a lot of them, I think we should publish more. But we are now confident that if the Polywell reactor works as we envision it based on some of the models that we have, it can turn into the very cost-effective fusion power reactor that can be built kind of in a relatively short period of time. So that was, and we didn't see any engineering showstoppers during that exercise, which was another very important finding. After that, we start looking for some funding to build the next system, while we also start interacting with some of the plasma physicists who specialize in computational simulation about how the plasma behaves. With the high-performance computing platform, it would be almost silly not to consider that avenue. So we've been interacting with several different groups. And then last year and a half, we start working with the groups at Catholic University, that's in Belgium, try to collaborate with them to develop a virtual Polywell fusion reactor. And that's been very fruitful. So that's the main thing that we did, is basically survey research on engineering side of it and economics as well. And then we also deeper into the fundamental physics with the help of the numerical simulation. So numerically speaking, I think we're about a year to 2 years away to have a virtual Polywell machine that we think that can demonstrate break even.
So you've collaborated with a university and you've had them build these virtual machines on the computer. Can you talk a little bit about the software that you're using to do that?
Last year and a half, we've been working with our collaborator at Catholic University in Leuven, that's in Belgium. We use a version of the particle in-cell plasma code known as XSim. It's an acronym for the energy-conserving semi-implicit model. XSim was developed by the Catholic University team, and they're based on the previous work known as IPIC3D, which is implicit particle code 3D. IPIC3D is an open source that people can download it. It traces its root to the plasma simulation effort at Los Alamos National Laboratory back in the early 1980s. That code has been a tremendous help for us. It worked really well. The key difference between the XSim code and the IPIC3D code is XSim conserves total energy of the system very well, thus make the code far more stable in a very challenging environment. So the study that they did is actually published. They were able to demonstrate that the XSim code conserved energy approximately about 1 parts for 10 to the 16 per each time stat compared to their previous work on IPIC3D, which was about 1 parts per million. So there's a huge jump in the ability to conserve the energy. The ability to conserve the energy in the XSim was pretty impressive, actually. Normally, IPIC3D is good enough, and there's a few papers the group published to simulate many interesting plasma phenomena like solar storms and magnetic reconnection. EMC2 actually worked with them about 5 years ago to simulate the Polywell plasma using IPIC3D. And we found that it wasn't working well. Now looking at it with the development of the XSim, it looks like being able to conserve the total energy of the system is a key to make sure that this very high density plasma is well simulated. So having this upgraded version of the code was critical. So we're very happy, and that was one of the key difference between XSim and IPIC3D. Over the next year or so, we plan to share some of those findings, and eventually we'll also make the XSim available for the public to simulate other fusion devices. That would be a great asset for the plasma physicists. So simulations are getting better, but we had better luck this time. It's much better parallelized than, say, 5 years ago. I remember when I was a graduate student back in Princeton, I ran some plasma physics code based on the fluid simulation. It was for the plasma diverter for ITER, and I remember using tens of thousands CPU to 100,000 CPU, but I was a grad student, so my computing time was very limited. Now computers are just so much better. The high-performing computing now uses 40,000 cores. Both XSim and new kind of the latest iteration of the IPIC3D now can tap into those enormous capability of this parallel processing, so they can divide the domain into many smaller domains and solve them, so you can actually look at the plasma in a very, very high resolution case. I was very pleasantly surprised at how powerful that was. So in some simulation cases that we now look at the plasma phenomena below electron gyro radius. And that's actually one of the most fundamental parameter in the magnetic fusion device.
Are you currently simulating, or are you finished simulating? And if you are finished simulating, what are your next 6 months? What are you planning to do next?
Obviously, understanding fusion device require a lot of different levels. So the first part is, let's look at all the data that are available. Let's look at what we learned out of that PRX experiment. Let's look at what we know out of the WB6, 7, and 8. And then we also went back to what people did in 1960s and 70s in high beta cusp experiment. A lot of them, they use these equilibrium magnetic field, not the vacuum magnetic field, to confine plasmas. In our case, to confine energetic electron beaming. So we went through those, and now I'm pretty happy to say that we understand. We can reproduce those results in a simulation. We know how that works. For example, those energetic electrons get confined inside a wiffle ball. So we're very happy that we can simulate the wiffle ball. We are now started the new project. So the second part of the project was we want to simulate so-called potential well. So you can think about Polywell as a combination between wiffle ball and basically a fusor. So make sure the code can accurately simulate the electric field at a thermonuclear plasma condition. There are codes that are available to simulate the electric field in the plasma very well. However, those cases, the plasma density is typically very low, like the electrostatic confinement device, where the plasma density is only about 10 to the 7, 10 to the 8, or 10 to the 9 particle per cubic centimeters. Those are well done. However, they are not in the thermonuclear condition. To generate the nuclear fusion energy, you have to be looking at plasma condition that is at least 10 to the 14 per cubic centimeters. We're looking at about 1 million times denser plasma. There, solving the Poisson equation accurately require a lot different approach. We can produce the wiffle ball in our simulation. We're now developing electrostatic potential well within the wiffle ball. It really pushes us to the boundary of what the numerical simulation can do. We hope to see that project done in about 6 months to a year. If we finish that, we now can begin developing a virtual Polywell fusion reactor that we can show Q=1 break even. So that's our goal. And obviously demonstrate it, make sure that people understand will require a significant amount of the work on our end. But first thing first,
what resources do you need to continue that work? Are you set with the amount of people you have, the funding level you have, the software and tools that you have, or would it be nice to have something else?
In my view, and most people will agree, is fusion research by the government is now focused largely on ITER experiment. That makes it very, very difficult to find public funding. So that's always been a struggle for us, and I'm sure that's a struggle for pretty much all alternative fusion concept. We had a reasonable support last couple of years from the private investor, and we're currently in the process of asking some additional funding from the existing one as well as some new ones to support that. Because from my end of it, we're looking at about probably close to $1.5 to $2 million over the next 2 years. With that money, I want to build a virtual Polywell machine that will do net fusion energy generation. The criteria is not only we do that, but we also have to generate enough data to convince others that we really have developed the blueprint for the Q=1 Polywell fusion reactor. So that, I think, is about 2-year project, total close to $1.5 to $2 million, which will support our team. Our team has about 4 people, and I'd like to increase that number to about 5 to 6. And I'm sort of hopeful that we will find some people who share some of our enthusiasm and understand the progress that we made. At some point during that 2-year period, I'd like to start a test experiment to check the accuracy of the code. You can build this thing in a virtual world, but that's not quite the same.
Can you talk about the current state of plasma simulations and how does it compare to, say, 5 years ago?
Plasma simulation has been in pretty rapid progress for the last 5 years. And I think it's tied to the big investment by government building this large-scale high-performance computing platform. And in some cases, even a private company like Amazon offer the cloud-based computing. So now the tools are better compared to 5 years ago. And obviously, plasma physicists has been making great progress in making their simulation tool better as well. On us, we had some great success over the last, say, about 18 months in simulating the Wiffle Ball and Polywell physics. So that's what represented tremendous progress in the simulation area.
You said in the last year and a half, you've conducted a number of virtual Polywell simulations. I think you said 40. If I was in a virtual Polywell, what parameters would I change to affect the performance of the machine?
In plasma simulation in general, what you're simulating is a set of equation combined with a boundary condition. Set of equation is Newtonian equation for the particle and Maxwell's equation for the electrical and magnetic field. Those equations do not change. What you change in those simulations is basically a boundary condition, which in real life is where would you place the magnetic coil, like how close they are, how far they are. What magnetic field strength you want to use is going to be about a Tesla. It's going to be 5 Tesla machine. And how are you going to heat this plasma? Are you going to inject the ion beam or the electron beam? Where would you inject it? With what kind of beam characteristic? So those boundary conditions represent what type of the fusion reactor is. So in a nutshell, one fusion reactor is a set of the boundary condition bounded by Newton and Maxwell's equation of the plasma. All you do in a virtual world is you change the boundary condition, and that represents how you want to build the nuclear fusion reactor in real life. And one of the most critical ones is how you arrange your magnetic coils and how you introduce your heating system. So where the electron beam heating comes into play, how you inject them, what parameters do you inject them. Those will determine the performance of your virtual machine.
So you're building a reactor in a virtual space, and then you intend to verify that the code gives you reasonable results. How do you intend to verify that the code is working properly?
So code will always give you numbers, no doubt about that. Can you trust them? What ground do you trust? That's a very, very difficult question. What we normally do is we run set of tests in both numerical part of it and physics part of it. So numerical part of it is you control, say, half the time step, quarter of the time step. You change the time step and make sure that your results are converged. You change the spatial resolution. You use 100 by 100 by 100 grid, or you use 200 by 200 by 200 grid. At some point, you expect the code to converge into the set of the result because it represents the real machine. And real machine should not depend on how many grid points you use in the code as long as you have sufficiently high number of them. Another one will be a time step. You choose your time step. So those are the standard numerical technique that you have to use. Next set of tests is a physics test. There has been reasonable set of physics data that we have in the Wiffle Ball machine that we have from WB6, 7, and 8. There has been number of papers that published using a high beta cusp plasma physics experiment. We changed the parameter space of the code to match some of the old results that we already have and start watching them reproduce the result that was reported or observed in the experiment. Does code actually give you the value that matches a reality? And another thing that we do is we change magnetic field strength, plasma temperature, and look at how the plasma behaves and make sure that it fits our physics understanding of plasma. And it has to go through those tests. To be careful. However, at some point, You have to stop the simulation. You have to build an experiment, take those parameters like the coils. You build a machine and you have to compare the key parameter of your plasma performance, like temperatures and densities. And you have to demonstrate that those do quite well. Now, instead of building a series of experiments, say like 5 or 10 experiments to produce so-called scaling law to predict how fusion device will work, now we place those scaling data with 100,000 line code. You run those code to generate your numerical scaling result, and you start filling those scaling data with selected points and experiments. If you do that, you can scale that toward a fusion power reactor. To me, that is real change in paradigm. Like, for example, before we build ITER, or decide to build the ITER, fusion community went through 20 to 30 big tokamak experiments over the span of 20-some years, and probably several billions of dollars. Now imagine that you will do the same exercise in your virtual fusion reactor. You will go to those different size, different operating condition, different boundary condition. It will generate models how you build the fusion reactor. If you do that, and if you have great confidence, say 10% or 20%, you don't have to build 20 machines. You will build basically 1 or 2 test machines to check your simulation that will allow you enough confidence to build the power reactor.
That is really exciting. The concept that you could build all these machines in a virtual world first and then build the one that seemed most likely to result in fusion. Do you have any advice for young people that are trying to get into this field?
I think it's actually a great time. Encourage young people to join this endeavor. This is one of the most important research topics that we could take. Fusion always had the stigma that it's always 20 or 30 years. I think things are changing. To me, you make major progress when you have a right tool. You can build iPhone when you have a variety of the components that you need, when you have certain technologies that come together. Fusion has that. We have incredible electronics that you can control. We have wonderful plasma beam sources, radio frequency heating, great system and materials that can withstand extremely harsh conditions. What has been missing since the days of the plasma physics is being able to understand the dynamics of the plasma at a very fundamental level. In a sense, plasma physics represent highly coupled nonlinear differential equation. We as a physicist or the mathematician do not have a good tool to solve. So we always make some approximation, assumption to simplify the equation. With the development of the computer, we're starting to be better and better to solve this nonlinear equation that describes the plasma physics. My understanding is in chip manufacturing, where the plasma are used, dynamics of the plasma in manufacturing process are relatively well simulated now with the machines that we have. And it's because they are inherently less dense, about 100 times to about 1,000 times less dense than what we have in a thermonuclear fusion reactor. Why does it matter? Because a coupled nonlinear equation, having more plasma density makes the equation harder to solve. So if you're solving at a density of, say, 10 to the 11 per cubic centimeter and try to solve the density at 10 to the 13 or 14 per cubic centimeter, it becomes a lot harder problem. EMC2 had great luck in being able to simulate the Polywell plasma in a thermonuclear condition. That was on the order of 10 to the 14 per cc at 1,000 electron volts or more. I think we are now seeing the change. We can start looking at these thermonuclear plasma with a simulation. It will be an incredible tool because honestly, building a machine is a very expensive endeavor and it takes a long time. It's not the most efficient way to actually explore very large parameter space to make a fusion reactor possible.
That sounds great. Final question, is there anything else that you would like to add Anything we didn't talk about, anything that you think people should know when they listen to this?
I think it's time to be cautiously optimistic because fusion is a very difficult problem. To do fusion, the first thing you must do is heat the fusion fuel to about 300 to 500 million degrees. Not easy, but you can do that. Now the next question is, you invested enormous energy to create these high temperature plasma. You have to make sure that heated fuel stays inside your reactor until they undergo fusion reaction. That is where the confinements are. Problem of that lies from the fact that fusion cross-section is very small. So, for a fusion reactor, that is a 10-meter machine, you need to have fuel to move back and forth inside your reactor long enough, approximately 10,000 kilometers. That's about the average time they need to travel to create fusion event. Those are difficult. That's one of the core reasons why the fusion took so long. Now, with those tools that we have, especially in the numerical simulation, I think it's a great time to get in because we're at the cusp of understanding plasma in a thermonuclear condition. In a thermonuclear fusion condition, the densities are approximately 1 times 10 to the 14 per cubic centimeter. Temperatures tens of kilovolts, that's where we can be looking at. Once we get to understanding those, people are creative, people are innovative. So given a right tool, I have no doubt that there will be a good chance somebody will find a way to build this numerical fusion reactor in the next 10 years or so. If they do that, building one based on that blueprint will be a lot more straightforward task. And if they manage to put it in, we can start looking at fusion power as a reality. So I think being optimistic and being excited, I think is a worthwhile effort for people to be in.
That's where we'll leave it. I really appreciate your time, and thank you so much for doing this.